Hello guys, welcome to this session. Unit 4 of course Supply Chain and Logistics Management has two parts. First part deals with sourcing and revenue management decisions, which we have already learned. In part 2 today, let us learn network design in the supply chain. We already know that supply chain consists of all the stages involved directly or indirectly in fulfilling the customer request. It includes customers, wholesalers, distributors, manufacturers, suppliers, and so on. In each stage, it includes all the processes, operations, resources that are needed in receiving and filling a customer request, be it product development, be it marketing, operations, manufacturing, distribution, customer service, anything and everything come under the scope of supply chain. If we consider one of the stages, say manufacturer, the supply chain forms a complex dynamic network system between the manufacturer and its upstream players, that is suppliers, on one side. On the other side, it is the network between the manufacturer and its downstream players, warehouses and markets, retailers, etc. So today let us learn the role and classification of network design decisions. What are the factors influencing these decisions? Let us throw some light on strategic framework for network design decisions. Also, we will analyze models for facility location and capacity allocation, and finally the role of IT in the network design decisions. Before entering into this, supply chain management deals with the three types of flows through supply chain, namely information, product, and funds. Supply chain manager needs to take many decisions relating to these flows to be efficient and effective. These decisions fall into three categories or phases. They are supply chain strategy or supply chain design, supply chain planning, and thirdly, supply chain operations. Out of these, supply chain design decisions are very important as they decide the supply chain's configuration, in the sense the structure, which and all stages should be there in the supply chain. In each stage, how many players should be there, and the decisions which are taken in this phase are valid for years, for long time, more than year at least, and they are very expensive to alter on short notice or frequently. Next, let us understand what are supply chain drivers, because design decisions set constraints for supply chain drivers. Supply chain drivers determine performance of any supply chain. They drive the supply chain towards excellence. They are used in the design, planning, and operation of the supply chain to achieve right balance between responsiveness and efficiency that meets the best needs of the customer company's competitive strategy. So let us understand what is the meaning of efficient supply chain, responsive supply chain, and competitive strategy. Efficient supply chain is able to deliver the products at the low cost. Here, while doing every activity, focus is on cost reduction. Whereas responsive supply chain is capable of responding quickly to the changing needs of the customers. Responsiveness is an important characteristic feature of responsive supply chain, which is defined as the ability of the supply chain to respond swiftly to changing customer needs. For example, Let us consider the product personal computer. In the market, the two players let us consider, one is Dell and the other one is Gateway. The Dell supply chain allows the customer to customize his uh, personal computer out of several thousand configurations that are available in the Dell website. And then this will be later delivered to the customer within days. So this mass customization makes the Dell supply chain very responsive. Whereas you consider the Gateway supply chain, Gateway sells its PCs through the retailers and hence only limited variety is available for the customer to choose. Obviously, the customers expect then the low cost. So here cost is prioritized as far as gateway supply chain is concerned, hence it is an example for the efficient supply chain. Mass customization and high variety is uh, the most focus for the Dell supply chain, and hence it is an example for responsive supply chain. Now let us see what is the meaning of company's competitive strategy. A company's competitive strategy defines, relative to its competitors, a set of customer needs which it seeks to satisfy through its products and services. Consider an example of Walmart, an American multinational retail corporation that aims to provide high availability of a variety of products but at the low cost. So, is its competitive strategy is high availability and variety. But this supply chain is an example for efficient supply chain because it focuses on low cost. Whereas consider the other American supplier, McMaster Car. It supplies MRO products. MRO stands for maintenance, repair and operation. It places greater emphasis on product variety and least response time, obviously at the high cost. So this McMaster car supply chain is an example for responsive supply chain, and competitive strategy here is product variety, high product variety and least response time. What is the meaning of response time? It is, for example, for a manufacturer, it is the time elapsed since the receiving of the order from its customer till it delivers the product to the customer. Now, in today's session, let us see one of the important drivers, that is facilities. Which are the drivers of a supply chain? Facilities, transportation, inventory, information, sourcing, and pricing. Out of these, let us focus on facilities today. Facilities are the locations where production takes place, either or inventory will be stored. They give answer to the question where in the supply chain. So correspondingly, we have two types of facilities majorly: manufacturing facilities and inventory facilities. Whenever a company newly starts its business at new place, number of questions arise. For example, consider Indian automaker Tata Motors wanted to start its uh, car, nano car, in 2003. So the important questions in front of it at that time were where to locate the facility, what should be its size, what should be its role. Network design decisions will answer to these important questions. These decisions become still more important as we are moving from local market to global market. Since these decisions are design decisions, they play very important role. All network design decisions also affect each other. To know the significance of these decisions, I'll give an example. Toyota, it's a Japanese multinational automotive manufacturer. Today it has plants worldwide. Earlier, it had plants, but each plant used to serve only the local market. Each plant used to serve only the local market. And in 1990, Asia went into recession. There was economic crisis. So the plants available in Asia had production capacity, but there was no demand. No market for the production being done in the markets, in the plants, because plants were serving only the local markets, and all the Asian local markets were in recession. This hurt the profitability of Toyota at that time. So later, after 1997, they added flexibility to their plants so that the plants could serve along with the local market also to global market. So this response to local as well as global markets, addition of flexibility changed the profitability of Toyota and its effectiveness as well. Network design decisions are classified as facility role, facility location, capacity allocation, and finally market and supply allocation decisions. Facility role decisions. These decisions answer to the question, what role should each facility play? Based on the processes performed, facility can be manufacturing or storage facility. Within the storage facility, it can be a retail facility or the wholesale facility based on whether it is used for small or large storage. For example, consider petroleum products. They are extracted from crude oil, say Indian oil or Bharat Hindustan Petroleum Industries. They use different types of facilities. First, the huge refineries where the petroleum products are extracted from crude oil. Then the large depots where the petroleum products and the diesel or the petrol are being supplied to railways or something like that. Then it will be also transported to small depots which we find on the highways or on the roadside, wherein we get our vehicles fueled. So in the complete system of petroleum products, we have huge refineries, we have huge depots, and we have retailer outlets. So when we go for a new facility, we have to be clear with its role. Next comes facility location decisions. These decisions answer to the question, where should I locate my facility? Very important because these have a long-term impact on a supply chain performance. Because once a facility is built, altering it to a different location or shutting it down is a very expensive offer. Consider retail facility, say for example, here the role is customer interaction. So obviously should be located very close to the customer, but not always, depending on whether the supply chain is efficient or responsive. These decisions have to be taken. For example, Walmart is not having any of its retail shops very close to the customer, not in the crowded area of city at all, because Walmart's model want to fulfill the customer request at the least cost. The supply chain is efficient driven. So it will try to keep the cost of the site facility all lower so that the costs that are saved can be transferred to the customer to attract more and more of them. On the other hand, 7-Eleven Japan, a famous food store, locate their facilities right in the crowded areas of the city so that the customers can easily walk into the facility. Coming to manufacturing facility, how to take the decisions. we have to decide based on the type of the product. Suppose if we consider small products like plastic bottles or buckets, then transportation of such products is cumbersome, hence can have such facilities close to the customer. But if we consider the big products like automobiles, cars, scooters, motorcycles, etc., throughout the country we have centralized few facilities, hence the location of such facilities close to the customer is not possible. But poorly located facilities sometimes will have definitely adverse effect on the profitability of the supply chain. For example, Amazon.com. Earlier, it had its single warehouse in Seattle in United States, but it found it to be not cost effective and hence added some more warehouses. Next decisions are capacity allocation decisions. Once again, very important area of decision making. They answer to the question what should be the size of the facility. Arbitrarily, one cannot decide the size. There should be a logic based on whether it is a huge facility or a small outlet or a depot, the medium scale, something like that. They once again have significant impact on supply chain performance because uh, they affect the different other costs. But compared to location costs, these can be altered a little bit more easily. Allocating too little capacity to a location results in poor utilization and higher costs, and allocating too much capacity to a location will affect the responsiveness if demand is not satisfied. Coming to the last type of decision, that is supply source and market allocation decisions. These are also very important decisions because they affect the total production, inventory, and transportation costs incurred to satisfy customer demand. Consider a manufacturing facility, for example. It has on its left side the supplier, on its right side the market. These decisions help in answering which suppliers have to supply to which plants and which markets have to be served from which plants. These decisions should be reconsidered on a regular basis so that the allocation can be changed as the markets grow. But for this to happen, facilities should be designed flexible so that changes can be incorporated easily. As I already mentioned, Amazon.com built new warehouses and increased the number of facilities as its customer base grew. Let us see now the factors influencing network design decisions one by one. First, strategic factors. As I already mentioned, competitive strategy refers to a set of customer needs which a firm claims to satisfy through its products and services. A firm's competitive strategy has a significant impact on network design decisions. Firms that focus on cost leadership, such firms are called as cost leaders, they claim the market, they capture the market by keeping the cost of their products low. Such firms tend to find the lowest cost facilities, though customers are not easily reachable. Whereas the firms that focus on other factors other than cost, such firms support responsive supply chain and such firms go for the setting up the facilities very close to the customers though cost is high. For example, many apparel producers in 2005 moved their manufacturing units out of US to low cost countries such as China, India, etc. to reduce the cost. Whereas Zara, a famous Spanish apparel manufacturer, built its production facility in Portugal and Spain, though cost was high, just to respond quickly to changing fashion trends in Europe. And this responsiveness has allowed Zara to become one of the fastest growing apparel retailers in the world. Next is technological factors. If production technology displays significant economies of scale, here economies of scale is the plural of economy of scale, meaning doing any activity by keeping the cost low. It is the characteristic feature of efficient supply chain. So, if production technology displays economies of scale, few high capacity locations are most effective. Whereas, if production technology supports other factors than cost, then large number of locations close to the customers is better. For example, computer chips, for which factories require very large investment. So better to go for few high capacity facilities to have. Whereas if facilities have lower fixed costs, then many can be preferred. For example, bottling plants for Coca-Cola. They don't need high fixed cost. So just to reduce the transportation cost, many bottling plants all over the world can have just to serve the local market. Next is macroeconomic factors. These factors are external to the firm and governed by the governing bodies of the place where facilities are located. These include taxes, tariffs, exchange rates, etc. Soon after independence in India, when manufacturing started, trading was totally local in the sense raw materials have to be procured from places within India, manufacturing has to take place in India itself, and markets in India only have to be served. But in 1990s, major economic reforms took place which led to globalization and liberalization of trading. Hence, global trade was encouraged. As a result, macroeconomic factors became more and more significant and started influencing success or failure of supply chain network. Next is political factors. Companies always prefer to locate facilities in politically stable countries where the rules of commerce, ownership are well defined and with clear legal systems. Because political uncertainties, if exist, then things become unpredictable for the firms to develop the policies. Next is infrastructure factors. The availability of good infrastructure is very important factor for locating a facility because poor infrastructure adds cost to the actual cost of the product and increases the cost. Key elements to be considered here are availability of site, labor, proximity of rail service, airports, seaports, highway access, power, water availability, etc. For example, global companies have located their factories in China near Shanghai, even though these locations don't have the lowest labor or land costs because rather than cost, availability is more important. Next, coming to competitive factors. Here, companies see for the competition, competitors' strategy, size, and location. When we look at competition, there are two possibilities: positive competition and negative competition. For example, if we consider the jewelry shops in major cities, the jewelry shops are all situated side by side in one street itself. Compared to shops which are located in isolated places, these shops in markets provide positive competition because all customers come to buy the jewelries to the markets rather than to the isolated shop. Reason is obvious, many options are available. Therefore, positive growth and relation of all facility owners take place. For the newcomers, uh, this is advantageous because they get the benefit of positive competition. So the markets are already set up. There is no headache of attracting the customers, so they prefer the markets once again. In the similar ground, we can think of auto manufacturers. Uh, to name a few, Faridabad in Haryana, Pune in Maharashtra, Sanand in Gujarat, Narsapur in Karnataka have developed auto hubs actually. This is because they provide local ecosystem best customized for auto manufacturing. So, positive competition helps for fast business growth. Knowing this, newcomers come and easily set up their business. Similarly, Buddy in Himachal Pradesh is providing local ecosystem for pharmaceutical products. There is another issue. As a newcomer, when a facility needs to be set up, places like Gurgaon, Faridabad, Noida, Bangalore, etc. are the choices at the first place. But in these places, logistics and infrastructure costs are very high because they have already found high level of success due to excessive logistic facilities. But for the beginners, high cost of setting the facility or running the facility is not that favorable. So this also issue becomes prominent while deciding the network design. This is regarding the location of the facility. Next, coming to number of the facilities. The number of facilities have impact on inventory, facility and transportation costs. As the number of facilities increase, inventory and facility costs also increase and transportation costs decrease. So, considering all these factors in a combined fashion, final conclusion regarding the network design has to be made. This slide shows the relation between response time and number of facilities. Response time is taken along y-axis, number of facilities is taken along x-axis. We can see that as the number of facilities increase, the response time decreases. For example, if we consider a point here corresponding to this, number of facilities is very less, whereas response time along y-axis is more. Whereas if we consider a point over here corresponding to this, number of facilities is more but response time is less. As I already mentioned, response time is the time elapsed since the receiving of an order till the products are delivered. For example, for a manufacturer, it is the time elapsed from the receiving of order for producing a particular product till that product is delivered to the customer. This graph shows the relation between the costs and number of facilities. We can make out as the number of facilities increase, the inventory costs, there are various types of costs that are incurred in a supply chain. In particular, if we consider inventory cost, as the number of facilities increase, inventory costs also increase. So they are directly proportional. Whereas there is a negative correlation between number of facilities and transportation cost. As the number of facilities increases, the transportation cost decreases. Coming to facility costs, obviously, As the number of facilities increase, facility cost should also increase. When we consider all the costs in totality, this slide shows the relation between the total costs and the number of facilities. Once again, number of facilities is taken along x-axis. All various costs are taken along y-axis. So in the combined effect, all the costs when considered, the total cost decreases as the number of facilities increases up to a particular limit. After that, once again, it starts increasing. This is because facilities and inventory costs increase as the number of facilities increases, whereas transportation cost decreases as the number of facilities increases. And also a relation between the service level in percentage with the number of facilities is shown. Obviously, service level increases with the number of facilities. Service level represents the product availability, and as and when the number of facilities increase, the product availability should also increase. As the number of facilities increase, the firm becomes more and more closer to the customers. Customers become more and more reachable. Next, let us see the framework for network design decisions. The goal when designing a supply chain network is to maximize the firm's profits while satisfying customer needs in terms of demand and responsiveness. To design an effective, successful network, a manager must consider all the factors which we have just learnt, such as deciding the location of the facilities, number of facilities, role and size of facilities, and allocation of suppliers and markets. Here, suppliers and markets are used in the generic sense. In the sense, for example, what I meant is for any facility, the facility which is just left to it, from where it receives the material, is called a supplier, and the facility which is to the right of it, to whom it supplies the products or services, is called customer. For example, for a plant, supplier, that is the upstream, very next upstream facility, is called supplier. So here supplier itself. And for a plant, very next downstream facility, that is warehouse, is called as customer. Similarly, for a warehouse like this, the plant is the supplier and market is the customer. Now, in this framework, all the decisions to be taken are arranged in the chronological order in the form of phases. So let us see in each phase how exactly the decisions will be taken. The objective of this phase is to define broadly different stages of the supply chain, and also what functions have to be performed in which stage, whether those functions have to be performed in-house or outsourced. What is the meaning of doing the tasks in-house and outsourcing? If a firm uses its capabilities and resources for to finish the task, then it is called as doing in-house. If any of the tasks are done by using the outside firm, by hiring the outside firm, then it is called as outsourcing. Going outside in the search of source is called outsourcing. We find many live examples around us. One of them is with respect to Apple. Apple gets its manufacturing of cell phone components done from China, Taiwan, and Korea. So, this is an example for outsourcing. Phase 1 starts with the clear definition of firm's competitive strategy. As I already mentioned, competitive strategy refers to a set of customer needs which a firm seeks to satisfy through its products and services. Once the competitive strategy is set, next step is to set the supply chain strategy which supports the competitive strategy and specifies the capabilities of supply chain network. Supply chain strategy meaning is it is the strategy which determines how exactly different tasks have to take place, how exactly raw materials have to be procured, what should be the nature of the manufacturing, how exactly distribution should take place, what is the nature of after sales service, all the activities how exactly to be performed will be determined by supply chain strategy. To achieve excellence, both supply chain strategy and competitive strategy have to go hand in hand. There should be strategic fit that is achieved to move towards the excellence. Further, once supply chain strategy is also set, managers should consider the other constraints and is there any scope for economy of scale, that is lowering the costs, something like that. So all those things have to be seen in phase 1. Now let us move on to phase 2. Once the stages are defined, the functions are to be performed are decided. Now the time has come for phase 2. The objective of this phase is to identify regions where facilities will be located, their potential roles, and the approximate capacity. For this, what are the inputs needed? So, first starts this phase starts with the forecasting of the demand. Also, understanding the nature of the demand, how far it is homogeneous or how far it varies across different countries, that is region wise. Next step is to identify is there any scope for economy of scale. Once again, wherever possible, cut the cost. And then what are the risks associated with the demand or political risk or any restrictions which are regionally imposed. So all these have to be considered while going for decision in phase 2. Now moving on to phase 3, objective of this is to select a set of desirable potential sites within each region where facilities are to be located. So we have already decided the stages, the functions to be performed, and then the regions where these stages have to be set. So now we have to consider within this region where exactly the site is to be located. In the sense, if it is efficient supply chain, sites have to be chosen somewhere inside, somewhere away from the city, in semi-urban area or outskirts or something like that. If it is responsive supply chain, then more number of facilities are possible and very near to the customer possible to set up. Once again, sites have to be selected based on analysis of infrastructure availability. Infrastructure requirements are divided into two categories, hard and soft. Hard deals with the physical components such as transportation services, communication, utilities, warehousing infrastructure, etc. Whereas soft deals with the level of skill of the workforce, the how far the region will receive the business, and so on. So now we have come to the last phase wherein exact location of the sites will be done. So in the third phase we have already shortlisted the sites. Out of them, best will be selected based on the various costs, local costs associated. So that is how, considering all these factors, the final network design decisions have to be considered. While making facility location and capacity allocation decision, a supply chain manager's goal is to maximize the overall profitability while providing customers with the appropriate responsiveness. As I already mentioned, responsiveness of a supply chain is the capability of the supply chain to respond to the varying uh, nature of the demand of the customer. Of course, responsiveness always comes with the cost. So, efficient supply chain cannot have considerable responsiveness. In a supply chain, revenues come only when the products are sold or only at the customer stage, whereas costs will be incurred in all the remaining stages: facilities, transportation of the goods, procurement of raw material, stock of inventories, labor. All cases will give rise to some costs. Before starting the analysis of these models, supply chain network design decision models, there is some information needed, should be handy. That information we have already seen as inputs in the framework when we considered. Same thing is listed here. First of all, location of supply sources and markets should be known. Also, the location of potential facility sites where the facilities have to be located should be known. Demand forecast, its nature, both should be known. Then the costs of facility, labor, material, transportation, then inventory, all should be known. Selling price should be known, as well as what are the taxes and tariffs as far as local, connected to local place. And then the response time of the customer. The meaning of response time here is the time that is the customer is willing to tolerate. Responsiveness is different from response time. Response time is connected to the customer since placing the order till he gets the product in his hands. The time elapsed in between is called response time. So responsive supply chain usually supports faster response time. Faster response time is one of the characteristic feature of responsive supply chain. Once this information is ready, either gravity models or network optimization models may be used appropriately. So let us see which one to use when. First one is gravity location model. Gravity models are used to find suitable geographic location. Gravity method is adopted, so that is why the name gravity location model. Few assumptions are made. Both markets and supply sources can be located as grid points. Using the coordinates, we can represent them on a plane. All distances are calculated as the geometric distance, and then the transportation cost grows linearly with the quantity shift. Now let us see the gravity location model. For that, few inputs are here, that is few symbols are used for those inputs. Let us see that. Actually, how it looks now. I have a facility like this. There are potential sites. Say for example 10 sites are available. Out of them I have to choose one for which the total cost is minimum. Always any facility when we consider, say for example a plant needs to be set up. So then we have to see the distances of those facilities which are in direct interaction with the plant. For example, if we consider this plant, the interactions take place with these suppliers. For a plant, on the left side we have the suppliers from whom raw material will be received, and we have warehouses on the right to whom the products will be delivered. So this particular plant is in contact with the suppliers, these two suppliers, and interacts with these two warehouses. So these distances are important, or they matter while deciding the location of this plant. Similarly for this plant, 2 more. So like that it goes on. So if to locate this particular plant, supposing if there are uh, 10 potential sites, then considering the costs, all the costs associated, we have to decide which is the best site. Say for example, a facility of an automobile uh, company, say showroom, to be set up in Bangalore. 4 potential sites have been already identified. One is in east, the other one on west, third is north, and then south. Out of these 4, one has to be selected. So we have to see what and all are the costs associated with the distances when we consider the sources and warehouses with whom that particular facility has to interface. And while considering all those costs, whichever is minimum should be considered. So these facilities could be either markets or sources, either markets or sources. I will go back now to the model. So let x and y be the coordinates of location selected for the facility, which I already showed. Let n be the markets or supply sources. Say for example, in this case we have markets or sources 5. 1, 2, 3, 4 and 5. Let x1, xn, yn be the coordinates of the marketplace n. I just showed it. For the first one, the coordinates are called x1, y1 because n is taking the value 1. For the second one, it is taking the value 2. So x2, y2. Similarly, for the third one, x3, y3 and so on. Let dn be the quantity to be shipped from facility to the sources. D, small dn, both the d's I have used. Capital D is for quantity, small d is for the distance. And Fn is the cost of shipping 1 unit, single unit, for unit distance, say 1 kilometer, 1 meter, something like that, between the facility and n. So when we multiply, supposing if, okay, before that, we need to calculate now what should be the location for where the facility has to be installed. So for that, what we are doing is, first we are calculating small dn using distance formula. This is called distance formula. xy are the coordinates of the facility. I'll show it with this network. Supposing if the distance between this facility which needs to be located and this source is to be calculated, then x minus x1 whole square plus y minus y1 whole square under the root will be the distance for it. Similarly for this, x minus x2 the whole square plus y minus y2 whole square under root. So in that way we are going to calculate dn. Now supposing if you multiply, Fn gives the cost per unit. If you multiply the entire quantity to be multiplied, then entire quantity to be shipped, then dn Fn will give us the total cost of transporting the complete quantity. And xn is connected to distance. So Fn is per unit distance into distance to be traveled will give us total cost associated with fxd. If you multiply total cost associated with the entire quantity to be shipped for the complete distance. So using this formula, similarly the denominator, using this formula get x coordinate, using this formula get y coordinate. Remember, x and y coordinates are connected to the facility which needs to be located. Now once these many values are present, I'll just tell you, because this is an iterative procedure, how exactly it goes on with the problem. I'll just show you with an example. Now so we can make out for all the markets and resources. If you calculate this and if you go for summation, then whatever we get is total cost. Total cost for any location is given by the summation of products of capital D, small d and capital F. That is cost per unit distance per quantity into distance into total quantity will give us the total cost for one facility, one location. Similarly, you do it for all the locations. If there are four, like the example of Bangalore, when I considered four locations, I considered east, west, north and south. Out of those four, the location for which I get the total cost minimum, I have to consider it for the final location. So optimal location is one that minimizes the total TC. So I just showed how exactly it goes with this coordinate points. This is the plane, XY plane, wherein the facility to be located, and these are the markets and resources where the with whom this facility has to interact. To make the things more clear, I have considered an example from the textbook, Supply Chain Management Strategy Planning and Operation by Professor Sunil Chopra. Now, let us say this. There is a manufacturer called Steel Appliances of high quality refrigerators and cooking ranges, has one assembly factory located near Denver, from which it has supplied the entire US. But with the passage of time, demand has grown rapidly, and CEO has decided to set up another factory to serve its eastern markets. The supply chain manager is asked to find a suitable location for the new factory. Three supply sources are considered. We can make out here supply sources are three. That means the new plant has to interact with these three supply sources for various raw materials, and it has to interact with the 5 markets situated in Atlanta, Boston, New York and so on. So it has to interact with these many places whose coordinates are given as X and Y. They are present here. Make use of this and calculate small dn. Capital Dn is given, that is quantity to be shipped, and transportation cost per unit per distance is also given. Multiply small dn with capital Dn and capital F and go for summation for all the markets and supply sources, and whichever is minimum that location you just select. How to calculate mathematically is explained in this slide. I already mentioned this model makes use of the solution procedure, makes use of iterative procedure. What is to be done? For each supply source and market n, evaluate dn. How to evaluate dn? We already saw in the previous example. Key xn and yn for the market and source will be given in the problem. So this will be given as data. XY to be calculated for the first iteration. I already told this is an iterative procedure. So first iteration, put XY value as 0. XY value for first iteration 0. These X and YN values will be given. Calculate DN for each one of the source and market. Once it is there, all these things will be given as data. You have calculated just now DN. Make use of it. Sum it for all the markets and sources after dividing, and you get the numerator. Similarly, you get the denominator, get X. Similarly, you get Y. Let us call this after first iteration whatever we get as X dash Y dash. These X dash Y dash values which we got after first iteration will become X and Y for second iteration. These things will become X and Y for second iteration. I repeat, for the first iteration X and Y values were zeros. Once we calculated x and y, let us call it as x dash and y dash. Once we calculated x dash and y dash, they become xy for the second iteration. Once again, second iteration, all the calculations will be done. That is small dn and then x and y. Let me call those values as x dash y dash for second iteration. And x dash y dash values calculated in the second iteration will become xy values for third iteration. So keep doing like this and stop when two consecutive xy values are almost same. For example, second iteration values x dash y dash and third iteration values x dash y dash almost same with a very meager difference, then those values can be considered as final xy for the facility to be located. Now we will move on to next model, that is demand allocation model. Once location decisions are done, so once this facility is located, further if we move, the demand allocation needs to be done. Once location decisions are done, next is task for the manager is to decide capacity allocation. In the sense, now the facilities are already in place. We have to decide the size of the facility, in the sense how much to be produced. For example, if a plant is located, say here a plant is located, decided already, Bangalore North. Then how much to be produced in this plant, that depends on what market it has to serve. In this case, it is serving these two warehouses. So what is the demand of this? What is the demand of this? Say for example 10 and 20. 20 plus 10, 30. 30 will be the production capacity of this plant. Like that, this allocation will be done in this demand allocation model. This comes under network optimization model. So in the question, if it is asked to find demand allocation model, then we have to follow the procedure which I am going to explain now. So capacity allocation model will give answer how much to produce. Will answer to the question how much to produce. So what are the key costs to be considered? Fixed costs, production, inventory and transportation. All the costs can be divided into based on the nature, fixed and variable. Fixed cost is one which will not vary with the quantity produced, whereas variable cost is one which varies with the quantity produced. For example, if a plant, if we consider a manufacturing plant, the rent of the building doesn't depend on how many we produce, so it is a fixed cost. If we have taken loan, the interest on that loan will not depend on how many we have produced, that becomes fixed cost. Insurance to be paid will not depend how many we produce, so once again that is fixed cost. Whereas the raw material cost depends on how many we have produced. Labor cost depends on how many we have produced. Those costs are variable costs. Also, while doing this allocation, we have to consider the customer service constraints in terms of response time. I already told you the tolerance of the customer. So are they willing to wait, or are they do they need the products in a very short lead time? That also matters. And demand allocation decisions can be altered on a regular basis. These can be altered on a regular basis based on whenever the costs change or whenever the markets grow. Now, network optimization model, in that demand allocation model we were looking at. So we will see the different components of this model. What is that this model is deciding? How much to produce. This depends on which market is served by the plant. Based on that we have to decide. or if we consider only the supply source and plant, then which supply sources are used by a plant. So here I have used two symbols, Xij and Cij. Earlier we had only N, that is the number of markets or the suppliers with whom the facility was interacting. Here we have two things, one is plants, the other one is markets. So the plants are considered as suppliers here, markets are considered as customers. Whenever something is supplied by a facility, it is called as plant, and whenever something is received by a facility, it is called as customer. Now X stands for quantity, C stands for cost. Suffixes are used, two suffixes are used here, I and J. I stands for plant and J is for destination. I is for plant and J is for destination or the customer or the market. So if there are, for example, before that, Xij is the quantity shipped from plant I to customer J. Cij is cost of producing and shipping 1 unit from factory I to market J. So if we multiply Xij with Cij, it becomes total cost of producing and shipping the entire quantity from I, the plant, to J, the customer. Goal here is to allocate demand from different markets to various plants while minimizing the total cost. So now let us see in detail the model. Here there are two things which are involved. One is factories or the plants, the other one is markets. So these are customers and these are suppliers. Now let the number of plants be N, number of markets be M. Supposing, for example, in this particular case, there are 3 plants and 4 warehouses. So I can take the value I, small I is for plant. So small I can take the value 1, 2 or 3. If small I is equal to 2, it's understood I am referring to second plant. If small I value is 3, I am referring to third plant. Similarly, small j, J stands for demand, warehouse or the customer. If j is equal to 2, then I am referring to second customer. If j is equal to 4, then I am referring to fourth customer, like that. M and N will take only one value. N represents number of factories. In the example which I just showed, the network, N was 3 and M was 4. So N will take only one value, 3, whereas I will take all different values starting from 1 till N. Could be 1, could be 2, could be 3. J will take the value, could be 1, 2, 3 and 4. Depends on which warehouse I am referring to. So these are the meanings of this N, M, I and J. I already mentioned C is the cost of shipping 1 unit from ith plant to jth destination, and Xij is the quantity shipping that is being shipped from ith plant to jth destination. So if we multiply, the product will be the total cost of transporting from ith plant to jth destination. And if we consider j is equal to 1 to M, M stands for markets, so all the markets being considered, and N stands for factories, so all the factories being considered. So this entire thing will consider from all the plants to all the markets, the entire quantity to be shipped, how much to be produced and shipped, what is the total cost incurred. And ultimate objective is to minimize this, because any cost when we want to minimize, so min is written, min stands for minimize. This is called objective function, written here. Why do we call this as objective function? This is actually a linear programming problem. linear because the degree is 1, and uh, we call this as objective function because objective stands for a plant, the objective is to maximize the profit or minimize the total cost incurred. That objective, if you write in the form of mathematical function, then we call it as objective function. So it is abbreviated as OF. Don't call it as OF, it is OF. So if mathematical formulation is asked, first you have to write the meaning of the symbols, then you have to write the objective function like this. Now, it is subjected to, ST stands for subjected to constraints. These are all the constraints. What are the constraints? So, we'll see the meaning of this one by one. I have explained in the next slide the same constraints. The first constraint is taken up in the next slide like this. Quantity shipped from various suppliers should be exactly equal to demand of the market. Consider a market, say J is equal to 1, first market. It will receive from a number of plants. The products it will receive from different plants, and here it is shown 3. First plant, second plant, third plant. X11, this arrow represents flow of material from first plant to first destination. X11 stands for quantity shipped from first plant to first destination. X21 from second plant to second destination. Similarly, the third one. Now, when we add all these, it should be equal to demand of this. Should not be more than that, should not be less than that. But each one, when they deliver, it can be less than that or equal to that. What I meant is, suppose demand is, say for example, 100. Demand of first warehouse is 100, that is market is 100. Then if X11 is equal to 10 and this is 20, 20 plus 10 is 30. Remaining all should be supplied by this plant, so it should be 70. So this is supplying 10, this is 20, then this has to supply 70. So that total, when we sum up, it comes to 100. Supposing that is the meaning of this, J is equal to, it holds good for all the market, so that's why J is equal to 1, 2 and so on up to M. Now DJ is the demand of a particular warehouse, and when we sum up all the quantities that is supplied from different plants, I is equal to 1 to N, N stand for plant, 1 to N, from different plants, all the quantities that is shipped when added up should be equal to demand of the destination. Graphically it is shown here. Similarly, second constraint would be quantity produced in the factory cannot exceed its capacity. Now, this is a plant which I have considered, first plant. It is delivering to 3 markets actually, first market, second market, third market. X11 is the quantity shipped by the first plant to first market, X12 from first plant to second market, and so on. When we add up all these, it should not be more than the capacity. For example, KI stands for capacity of this plant. If say I is equal to 1, first plant I have considered, K1 is equal to 50, then X11 is supposing 50, X12 is 20, 50 plus 20, 70 is already over, X13 should be equal to 30 to make the total 100, or could be less than that. Sometimes it is quite possible that all the thing produced will not be sent. So if that is the case, could be less than that. But the entire quantity, if you consider, should never be more than. That is why less than or equal to. So for a plant, given plant, say I is equal to 1, first plant, all the quantity that is supplied from the first plant to different destination. J is equal to 1, 2 and 3 in this case. So j is equal to 1, j is equal to 2, j is equal to 3. All xij, in the sense if I is equal to 1, 1, 1, x1, 2, x1, 3. When you add all of these, should be less than the capacity of the first plant. Similarly, it holds good for all remaining plants. Just a tip to easily remember, logic just now I explained. If you want some tip to easily remember, always remember that whatever comes here will not get repeated here. That means if you are referring to j here, you have to refer I here. If you are referring j here, and then you have to definitely refer I here. At both the places you will not have the same I or same j. This is just to recheck or just to remember easily. So this is the meaning of the constraints. We'll just go back to the same slide. I just explained what is the meaning of this constraint and what is the meaning of this constraint. This constraint is called non-negativity constraint. These two are called as structural constraints, whereas this is non-negativity constraint, which says that quantity shift can never be negative. I cannot say that I have shipped -2 tables, for example. It doesn't have any meaning. So quantity shift should be always positive or equal to 0. So these are the three constraints. This is the network. If asked to draw the network, simply don't draw without any labeling. When network is asked to draw, you have to mention which are the plants, which are the warehouses, and what is the meaning of this arrows and all those things. We will next see the model plant location. We are in optimization models. Plant location with multiple sourcing. So multiple sourcing means many sources are there. Where to locate the plant? Compared to the previous one, once again, this is the objective function. Compared to the previous one, we have something extra in this. This much we have already seen, so I will not explain again. So I'll concentrate on this. Strictly speaking, this is called fixed cost, this is called variable cost. This is variable and this is fixed part. So fixed part and this is variable part. I already told you what is the meaning of fixed cost, what is the meaning of variable cost. Variable cost, we already saw the explanation. Coming to fixed cost, both put together when we add, it should be minimized. So here the bracket comes actually minimize this much totally. Now what about this? What it says? It is quite possible that some of the plants may produce, some of the plants sometimes may not produce. Suppose sometimes it so happens ki fixed and variable put together of a particular plant is less than the variable cost or the fixed cost of some other plant. Say for example, if a plant is right in the middle of a crowded city, then all costs associated with that become very high. So it is possible that that plant can be closed and a plant which is situated somewhere at the outskirts functioning, so that total fixed and variable cost of that outskirt plant is much less than the one which is present at the center. So there is some mechanism, there should be some mechanism which makes this either present or absent. Means either 0, sorry, not that much, this much, either 0 or 1. So that will be taken care by this variable yi, which we call binary variable. We call it binary variable because it takes only two values, 0 and 1. If yi is 0, the meaning is the plant is not producing or close down that plant. So if yi is 0, entire this term becomes 0. So only term becomes 0 for that particular I value. Suppose I value, if there are two plants, I is 1 and first plant is closed down, then yi will take the value 0. So if yi is 0 for first plant, these values are 0, these value is 0, meaning no fixed cost of first plant should be considered because it is closed down. Fixed cost comes into picture only if the facility is running. So the facility is closed, no fixed cost for first plant should be 0. Whereas for the second plant it is there because y1, that is y2 will take the value 1. Once yi take the value 1, then this value will be present for that plant, so fixed cost of second plant will be considered in the total cost. So once the first plant is not there, its associated variable costs all should also become 0. Now after adding, you should minimize the total cost. Once again, all other things remain same. Ki is the capacity, n is the number of factory, number of markets, xij is the quantity shipped. Only new introduction is yi, which is a binary variable. So if this in this network, if this plant is closed down, then f1 will also be 0 because its multiplying term, that's y1, is 0. So that's how using this yi we control the fixed cost, either to be added if the plant is open or else 0 should be added if plant is closed. And we can make out there is constraint wise, this constraint remains same. The total quantity I have explained in the next slide. The first constraint, it remains same, total quantity shipped from all the plants to a particular destination when we sum up should be equal to the demand. Quantity shipped, the meaning is written here, quantity shipped from suppliers should be exactly, all the suppliers should be exactly equal to demand of the market. Mathematically it's written here. For example, if j is equal to 1, the first destination, if dj is its demand, then all the summation of all the quantity that are coming in from various plants, I is equal to 1 to n. N is 3 here. N is 3, 1, 2, 3. So for all the 3 plants, if the quantity that is coming in added up should be equal to demand of that destination. Similarly, it is true for all remaining destinations. The calculation is given here and graphically it is shown here. Coming to second constraint, quantity produced in the factory cannot exceed its capacity. So quantity produced in a plant, that is, for example, if mathematically shown here, if I is equal to 1 for the first plant, capacity is Ki, say for example 50. If all the quantity that is shipped from plant 1 to all the destinations are 3, so 1 to 3, if you sum them up, it should be less than or equal to capacity Ki. But what is this yi newly appearing here? Yi is a controlling factor which will control, controlling variable which will control whether that plant is open or closed. If yi is 1, then this value exists and it's equal to Ki because Ki into 1. So quantity shipped from that plant should be less than or equal to its capacity. Whereas if yi is 0, y1, say for example in this case for the first plant it is 0, yi can take only 2 values, 0 and 1. If it is 0, these terms become 0. So then the quantity shipped, totally quantity shipped from that plant should be less than or equal to 0. Equal to 0, okay, that says that the plant is closed. Less than 0 is not possible because this person will control immediately. Xij should be either greater than or greater than 0 or equal to 0. So that is why this particular constraint, together will this constraint will act appropriately. And this is the constraint saying that yi should take only 2 values, binary values. So that is how this multiple sourcing, plant location with multiple sourcing is functioning. Next is capacitated plant location model. This model is same as multiple sourcing model which we saw just now. The inputs are also same. The model is also same in the sense the objective function is same, constraints are same. So the plant with the capacities when given, location and allocation, how to be done, this model explains. So since the things are one and the same, I'll just move on to the next one. Now just see the difference. Single sourcing. Earlier we saw multiple sourcing. Now it is single sourcing. How exactly network wise it differs, I'll just show you. Now here, just see this network compared to the previous one. I will give 1 second for you. 5 seconds for you to decide what is the difference, to think what is the difference between this network and previously which we drew. Don't see the right side network. Okay, now if you have got the answer, very good. Here I have given what is wrong, in the sense, consider a warehouse. This warehouse should have only one source, that is this plant, this one. Whereas this plant can supply to more than one warehouses, that is fine. For example, this plant is already supplying to more than one warehouse. But if you take one warehouse at a time, it should be served by only one supplier. That is why this is wrong. This part is completely wrong. This is the difference between previous network and this network. Previous network we had this kind of thing. Now we are not supposed to have. This particular warehouse is being served by two plants. That is not correct. This, if this is a customer, this should have only one source. So this is wrong. Whereas here, this is a customer has only one source, this is a customer has only one source, this is a customer has only one source, and this is the customer having only one source. So that is the meaning of single sourcing. If single sourcing specifically asked, network should also be drawn very specifically and carefully. So we'll move on to the model now. What changes are there? Only the changes I'll just stress, other things we already know. Here the supply chain network has a market that is supplied from only one factory, referred to as single source. Why the supply chain manager prefers this kind of network? Because complexity involved is less, and then coordinating the network becomes very easier. So sometimes it cuts down the costs as well. So once again, the same mechanism is used, that is yi, the binary variable, is used to decide whether a particular plant is operating or closed. If it takes the value 1, that plant is operating. If it takes the value 0, then that plant is closed. X stands for the quantity shipped from ith plant to jth destination. Just see the formulation now. This is the objective function, and the variables which we use in the objective function, we call it as decision variable. Xij, Cij, particularly Xij, because we call them as decision variables because they decide, they help in decision making. That is why the name decision variable. Now dj is demand of jth destination, Cij is the cost of shipping from ith factory to jth destination, 1 unit of item, and Xij is the quantity. So per unit, if it is C into quantity X shipped will give the total cost of shipping from ith factory to jth destination. Like that, if we consider all summation of I is equal to 1 to m, j is equal to 1 to m, all factories and all destinations are considered. Now this is actually extra. This part is extra, dj. What it does, this I have already told, this is variable cost and this much is fixed cost. All put together, try to minimize. That's what the objective function stresses at. But here, why this dj is introduced? Xij, sorry, I told that quantity shipped, but actually in this particular model, X will not take that role. X is not the quantity to be shipped. Xij will take 1 if that market is supplied by a factory, and if not supplied, it will take 0. Means Xij acts as a binary variable. Can you make out? In this model, there are 2 binary variables mentioned here. Yi, as usual, for location decision, that is to keep the plant open or closed, and Xij whether that shipping takes place or not. So accordingly we have here this, can you make out, this will control also, because if we consider for a particular destination, that is for the customer j is equal to 1 first customer, then to that first customer all the quantities coming from all the plants, when we add when we consider the number of plants, Xij is either 1 or 0. If you add all, it should be 1. That means for any one plant it can be 1, for all the remaining it has to be 0. That's how it controls. Then if supposing yi is 0, then this part itself is 0. That means that factory is, that plant is not functioning. So the capacity should be more than or equal to the quantity shipped. That is what it is telling. Once yi is 0, the factory itself, the right side itself is 0, factory itself is not functioning, so there cannot be any quantity shipped less than 0. So this doesn't happen. If yi is 1, then only this equation holds good, means takes the values. So if yi is 1, ki into yi is ki, which is capacity of first plant. Say I is equal to 1, supposing ki will be k1, capacity of first plant. Capacity should be always greater than or equal to the total quantity shipped. How much is total quantity shipped? Here Xij can take either 0 or 1. If it is 0, it's understood from that plant nothing is getting transported. If Xij is 1, then it's understood entire quantity dj at once, andre only from that plant is getting transported. So that is how dj is appearing here specially. This particular constraint has got both the binary variables Xij and yi. So that's how single sourcing model is functioning. And this network to be drawn, when single sourcing network to be drawn, one has to be very careful because it has to be specifically drawn. Coming to the last model, locating plants and warehouses simultaneously. In the sense, this has got all the players. For example, I have shown the network like this. There are suppliers which are supplying to various plants. Plants will receive from the suppliers and also supply to warehouses. Warehouses receive from plants and also supply to markets. So XHI, there are many X variables. XHI stands for quantity that are supplied from supplier to plants. H refers to number of suppliers. I refers to number of plants. XIE from plants to warehouse. E refers to number of warehouses. So J refers to number of markets. XEJ from warehouses to markets. These arrows represent the flow of material, and this is suppliers, plants, warehouses and markets. So here itself I will explain the constraints. Constraint for supplier is that any supplier cannot produce more than its capacity. For a plant there are two constraints. Any plant, if you consider say plant number 1, first plant, cannot receive more than its demand. For example, 2 suppliers are supplying. If you add, it should be equal to demand. Similarly, plant 1 cannot deliver more than its capacity, andre more than the quantity it has received from the supplier. So warehouse 1 and 3, to 1 and 3 plant 1 is supplying, it cannot supply more than the quantity that it has received from the suppliers. Similarly, warehouse 1 cannot receive more than the quantity it needs, that is its demand. Similarly, warehouse 1 cannot deliver more than the quantity it has taken from the plants. So these are the constraints. Mathematically it is written here. Can you make out? Quantity shipped out of a warehouse cannot exceed the quantity received from the factories. So for E is equal to 1, it cannot be The quantity that is shipped cannot be more than the quantity it has taken. So like that for all, and there are two binary variables yi and ye, and these are the quantities cannot be negative. That's what non-negativity constraint says. Similarly, for supplier there is only one constraint, whereas for each one of the players later has got two constraints. One is regarding receiving and the other one is regarding delivering. For example, if we consider a factory, for a factory, the quantity which it has received and the quantity which it is sending, the difference between these two should be either greater than 0 or equal to 0. It cannot be less than 0. So similarly, for quantity produced, it cannot be greater than its capacity. So these are the various inputs that are being used. Yi stands for factory. It is, if it is 1, then factory is located. If it is 0, no. Ye for warehouse, if it is 1, it will be there, otherwise no. Similarly, quantity shipped from warehouse to market, from factory to warehouse, from supplier to factory. Very big formulation. After adding all this, you need to minimize. It is not minimize and only applicable to first term. So this is fixed cost of locating the factory. This is fixed cost of running the warehouse. If it is open, then fixed cost gets added up. If y is 0, then no cost, fixed cost for that particular warehouse. Similarly for plant, then these are the costs of shipping from supplier to factory, from factory to warehouse, from warehouse to market. And when we add all, and supply chain manager's objective is to minimize the complete total fixed and variable cost put together. So we have finished all the models. Now let us see what is the role of information technology in network design. An IT system, information technology, IT stands for information technology system, used, if it is good, then it makes the modeling of the network design problems much easier. Since it will be having add-ins, built-in tools, extra, specially, modeling becomes easier. It will have high performance optimization technologies which deliver a high quality solution and within shortest time. So the models which we showed, when you run with the for the real cases, real live examples, it takes lot of time to converge. So a sophisticated IT system is always better. Allows for what if analysis. Always demand is uncertain and variable. So for different demand values, what is its impact on the performance or on the cost. So this analysis can be done so that uncertainties are also addressed. It needs to be interfaced with, because it is not only the design that is ultimate. The design has to be next related to planning and operational software. So that is why this interface should become easier. So good IT system will make this interface easier. But there are also some disadvantages associated with these IT systems. Since decisions that are connected to network design are all strategic, I already told you decisions are of 3 types: strategic, planning and operation. So these strategic decisions are very important, because changing these decisions deemed as very expensive. So few of the factors when running supply chain network, we feel that it is hard to quantify. They are not quantifiable, intangible. For example, culture connected issues, quality of life, cost of coordination, All these things cannot be quantified, and once can't be quantified, cannot be included in mathematical, cannot be expressed in mathematical form, and once cannot be expressed, then the IT system fails to handle. So these relevant non-quantifiable factors have to be manually considered along with the results of the IT system. So, dominating players in the market today are IT technologies, Oracle, and SAP in developing this network design decisions. So, we have come to the end of this session. Thank you for your patience hearing. I have few assignment questions put here. Go through this YouTube video and then answer to these questions. Thank you.